in general, the spectral analysis of angle modulations is difficult. And it's difficult because of the nonlinear relationship between the information that we transmit, m of t, and the modulated signal s of t. Because of this, only some few cases can be analyzed. And one of these cases is the case of an angle modulation where the modulating signal is a sinusoidal carrier. And this is the case that we are going to analyze in this video. In this case, the modulating signal m of t is going to be a sinusoidal signal, but we'll have a different representation for m of t to later have a common representation for the modulated signal s of t. Here, for a phase modulation, s of t will be a sine with amplitude a, and for the frequency modulation is a cosine with the same amplitude a. For a sinusoidal modulating signal, it's very easy to compute the modulation indexes. For the phase modulation, it is equal to the product between the phase deviation constant and the range of the modulating signal, Kp times Cn, but the range for a sinusoidal is equal to its amplitude A, Kp times A for the phase modulation. For the frequency modulation is the maximum frequency deviation divided by the bandwidth in hertz, Kf times the range divided by B, the bandwidth in hertz, and the bandwidth for a sinusoidal function is relatively simple. It is equal to its frequency in hertz, that is equal to the frequency in radians per second divided by 2 times pi. Now, when we include these expressions in the definition of the term phi of t in the angle of the modulated signal, we have a common representation for both the phase and the frequency modulation. For the phase modulation, we have Kp times the modulating signal, and Kp times the modulating signal is equal to Kp times A times the sine is equal to the modulation index times sine of the frequency of the modulating signal times t. And the same thing happens for the frequency modulation. In this case, phi of t is proportional to the integral of the cosine is a sine, the term that we have here is basically equal to the modulation index for the frequency modulation. In this way, we have a common representation for the term phi of t for both the phase and frequency modulation. This is the reason to have a different parameterization here as a sine or as a cosine for the phase and frequency modulations. Finally, for both modulations, it is possible to write the modulated signal as this expression: a carrier function, a cosine with frequency omega c times t, and with the phase argument equal to the modulation index times a sine with the frequency of the modulating signal m of t. Now, with some very simple mathematical manipulations, we will obtain an alternative expression for this modulated signal. First, a cosine can be written as the real part of a complex exponential, and we separate in the product of two complex exponentials the addition of the two terms that we have here. This term, the complex exponential of argument beta times a sine, is a periodic and very well-known function that has a very well-known Fourier series expansion, where the coefficients of the Fourier series expansion are known as the Bessel functions of the first kind of order n and argument beta, Jn of argument beta. By replacing this expression by the Fourier series expansion, we obtain this analytical expression, and rearranging the exponentials to write them together. Now the real part of this complex exponential is a cosine, and we get the alternative expression for the modulated signal. And in this alternative expression, we have an infinite addition of cosines. Cosines with frequencies, the carrier frequency plus n, determine this addition here, n times the frequency of the modulating signal, and the amplitude of the cosines are proportional to the Bessel coefficients J n of beta. Therefore, the modulating signal has a sinusoid with frequencies the carrier frequency plus n times the frequency of the modulating signal, and the amplitudes are the carrier amplitude times the coefficient Jn of beta. Although we have infinite sinusoids, infinite values for n, the 98% of the power is defining the effective bandwidth and is contained in a bandwidth given by 2 times the modulation index beta plus 1 times the frequency of the modulating signal. Here we can obtain the corresponding expressions for the phase and the frequency modulations, taking into account the definition of the modulation index for these two modulations, and the number of harmonics where this effective bandwidth is contained is given by 2 times the modulation index rounding to the floor, if this is a non-integer number, plus 3. Therefore, if we want to plot the spectral representation of an angle modulation in this case, we can compute the number of harmonics in the effective bandwidth. We know the frequencies, we know the amplitudes of these sinusoids, and the frequency response is a set of deltas located at the corresponding frequencies, the carrier frequency plus integer number of the frequency, an integer number times of the frequency of the modulating signal, and the amplitudes are the amplitudes of the sinusoids, AC times Jn of beta times pi. It's relatively simple to plot the spectrum for these signals.